Welcome back to my course Aspects of Biochemical Engineering. Now, in couple of lectures we are dealing with the living cells, and living cells both in the form of free cells as well as in the immobilized cells, and we discussed different processes like batch process and continuous process. And continuous process we have come across chemostat and the plug flow reactor. Now, this particular lecture is something different because we are going to discuss a new type of process, what we call fed batch process. And I mentioned before that for the substrate inhibition, we usually prefer the fed batch reactor, because in that here I want to point out, in case of product inhibition, we usually prefer the plug flow reactor. So, now question comes how the fed batch system can be operated and how it can be analyzed. So, this I am going to discuss in this particular lecture. Now, first let me consider that what do you mean by fed batch process. Fed batch process means that the batch culture that is fed in the media either intermittently or continuously without removal of culture fluid. So, what does it mean? That suppose this is a reactor, am I right? This is a reactor. So, we start with small volume, and then this is the reactor, this is moving. So, there is the input, we may pass as a particular flow rate of substrate, but slowly so the liquid the height maybe increases, and when it comes here, then we stop the flow, then let the reaction complete, then we take the liquid out. So, this is the fed batch we are, and this feeding may be of two different types. One is variable volume, one is fixed volume. Variable volume means is slowly you can you have this, you can increase like this, you can have that, and fixed volume means with respect to time, you can keep on adding this some volume with this in this particular reactor. So, these are the things that we have usually used for obtaining very slow growth rate, resulting the substrate limitation, and can be operated two ways. One is variable volume, another is fixed volume. Now, question comes, how you ensured your substrate utilization is more. Let me analyze that. Suppose what I am saying that this is a reactor. Now, this is moving like this. Now, when you consider the batch process, what is the basing the feeding strategy we have? We have like this. We take the material, allow it to react, and then take out the material. Again, we have take the material, then allow it like this. This is with respect to time. This is volume. Am I right? This is the batch process. Now, if you consider the fed batch process, what is the strategy that we have? We have here also we have volume, and this is time. So, we start with some volume. I have shown you in the reactor. We start with some volume. This is the volume. Then we increase slowly, and they attains then another this volume. What is the final volume? Then we take the material out. Am I right? Then again we start this operation. Again we increase the volume. Again take it out. So, it is this is stepwise. We can operate the system. Another way how we can operate. So, this is the way you can find out. Another way that that now here one interesting thing is that if you look at the substrate concentration with respect to time. Now, substrate concentration will keep on decreasing. Suppose in this reactor you put your raw materials and allow it to react, then what will happen, that substrate concentration will decrease with respect to time. When it comes to minimum, then again you feed it. So, this is you can increase the feed like this. Now, here you imagine here you have the volume V1. Now, next when you add, this is V2. Now, when you add V2, this will be little concentrated material, am I right? So that you can have the substrate concentration what you have is 0, the same level. Again you can decrease like this, again you can increase like this, again you can decrease like this, again you can increase like this, and until and unless you reach the final volume. Now, if you look at the other type of strategy that we have, like S versus time. So, what we can do, we can first we start with the volume, let the reaction take place, and then we start feeding, the substrate decreases, then again we feed after we come here, this is S0 value, and then we continuous feed in the manner, so that your this value remain S0, and then finally when we reach the final volume, with substrate concentration decreases to this. So, this different type of feeding strategy we can use in case of immobilization system. Now, here we have given the example of the variable volume feed. So, we start with this volume, this is the start, then we increase little bit, you can see that value, and final volume we did it. Then when they reach the final volume, this is the final volume, am I right? Final volume. When it reaches the final volume, then we do the harvesting of the material. Now, question come how you analyze this system. Now, rate of flow, that flow rate, what is the unit of flow rate? What is the unit of flow rate? If flow rate is equal to volume per unit time, am I right? So, this is exactly we have shown here dV by dt. This we can write dV by dt. dV is the change of volume, this is per unit time, this is called flow rate. Now, we are adding this substrate at a flow rate F and initial substrate concentration is 0. So, what we can write, change of volume V, what is this is initial volume might be you have V0 and final volume you might be having V. So, V0 to V, the dV equal to 0 to V dt, this is F into dt. This we can write in this form, and this is equal to V equal to V0 plus Ft, where V is the volume of the reactor at time t and V0 is the initial volume of the reactor. So, we start with V0 volume and then continuously add it to make the volume up to Vt. So, this is how we can find out the volume of the fed batch reactor. Now, let us discuss about the kinetics of the fed batch cell growth, how we can discuss the kinetics. Now, here we can consider the pseudo steady state condition. What do you I told you in my previous couple of lectures that pseudo steady state means not exactly steady state. We assume that it is approaching towards the steady state condition. That is the pseudo steady state tends to. As for example, sometimes we say that x, suppose we always say that x tends to or s tends to 0. S tends to 0 does not mean s equal to 0. S tends to 0 means it tends to 0. It is something similar that pseudo steady state also like this, it is tends to steady state condition. Now, quasi steady state condition is added, surface added equal to surface consumed. So, if you do that, then and only then you can keep on adding the substrate, and because you have to maintain the substrate concentration below the inhibition level. Suppose above this level we have substrate inhibition. So, to maintain this inhibition level, we shall have to add the substrate in a manner that whatever the substrate that is consumed, that substrate you have to add. So, that this and when final volume reach, then you stop the feeding, then substrate concentration will keep on decreasing with respect to time. So, what you can write the mass balance, how you can write, this is the rate of input equal to plus rate of cell generation equal to rate of cell output plus rate of cell accumulation and cell death. Now, if you consider this is the steady state condition, this is if you consider that unsteady state condition, then because you are adding, you are not taking it out from the system. So, what is the rate of input f into x 0? This is here, let us assume this is x 0. That this is what is the growth that will take place, mu into x is the dx by dt. So, this will be dx by dt into v, am I right? This is the volume will be take place. The output will be 0, there is no output in the fed batch reactor, and rate of accumulation, everything is accumulated in the system, cell cell accumulation can be expressed like this, and we can assume that there is no cell death occur in the system. Then we can assume this is x 0 equal to 0 when we have sterile feed. If we have sterile feed, then we can assume that no cell present in the media. Then we can assume that this is equal to 0, and then this equal to then we differentiate this x and b, then we can x dv by dt and v dx by dt. Now, dx by dt, if we assume rate of cell formation, that is assumed to be 0, that is not the changing, then constant, then we can write this is equal to x into dv by dt. Now, this is equal to mu 1 by v dv by dt equal to f by v. So, f by v, what is f by v? F by v is the dilution rate that we have already seen. This is nothing but equal to the dilution rate. Now, again, now here we have what we have d equal to. So, this is equal to, we can write that mu equal to d f by v 0 by f t, this equal to, right. Then from the Monod equation, what is mu equal to mu max s k s plus s. So, we can bring this, and we can by using this equation we can easily find out what is the state, what is the substrate concentration at time t, that we can easily find it out here. Then now the biomass concentration at time t can be given by x. X is the total cell mass, and x is the cell mass concentration. Then x t is the total cell mass divided by volume is the cell mass concentration. So, quasi steady state condition, the dx by dt we assume to be 0. Then we can write dxt by v by dt equal to 0. Then we can differentiate this, we will get this equation, and this is the formula that we have. And then this equation we can write in this form, dxt by dt equal to xt by v dv by dt equal to f into x. This we can analyze, and we can write like this. Finally, we find that x total is equal to x 0 plus this we can write x t equal to x 0, x t minus x 0. So, this we can also write in the form of this also, this we have seen before also, that this is how it is related with the substrate concentration. This we have done before with the help of Bill coefficient, we can find it out. Then now, when s equal to 0 and x 0 is much less than x t. So, x t is the total cell mass concentration is very high as compared to initial cell mass concentration. Then this equation, with this equation we can write this, we can neglect. So, we can write x t equal to x, this also we can neglect, then x t equal to y x by s into s 0. Then this equation if you combine, we can dx t by dt equal to f y x t by x 0. The integrating this form, we can have this equation x 0 plus f y x by s 0 into t. Now, this is the boundary condition, we can say at t equal to 0, x t equal to x 0. That condition we can have. Now, how we can find out this kinetic constant? By using the line of a buck plot, we can do that we can put 1 by d versus 1 by s, because by this line wave buck plot, by using Monod equation, we can find out the intercept will give you the value of 1 by mu max, and slope will give you the Ks by mu max. Now, this mu max value you put it here, you will get the Ks value of the organism. Now, let us discuss that another interesting feeding strategy that we have with the constant volume batch process. So, what do you mean that we are here in this case, what is doing that a very concentrated solution of limiting substrate is added intermittently at a very low flow rate and lower than the variable fed batch process, resulting in significant increase in volume. So, what does it mean? Mean that that volume we are not increasing much, only we are adding the concentrated substrate solution, just to maintain. As I told you that this S0 value we want to maintain constant with respect to time. So, you keep it constant, and then when it reaches the final volume, then it keep on decreasing like this. So, this is the constant volume feed. This is the another strategy that we have in the fed batch process. So, here the analysis we can do like this. Since the limiting substrate is acid intermittently, and rate of change of the cell mass depends on the flow rate, such that dx by dt equal to g into dx by s equal to, this is g into y x by. What is g? G is the substrate feed, that is gram per liter per hour. That is the, so you have gram per liter per hour. Now, what is this yield? This is the gram of substrate. Am I right? So, now what is this yield? This is the gram of cell per gram of substrate. So, this substrate will gather. So, you will give you the gram of cell produced per liter per hour. This is what we mentioned, that dx by dt. Now, cell mass balance can be written as that we have already shown this several times. The rate of input equal to plus cell generation equal to rate of output, accumulation and cell death. Now, here we can write f into x0, we have shown before. Then this is the rate of cell mass growth, the output is 0, no output here, this output is totally 0, and this is the accumulation of the cells, and we assume no cell death. Then we can write this equation in this form. Now, if you look at this equation, then we can bring it back in this form, that the volume, if we assume the volume is constant, the x0 tends to 0, then the above equation may be written as mu x equal to dx by dt equal to g into y by x. The mu will be what? 1 by x g y x by s. Now, 1 by x g 1 by x less than mu max, the limiting substrate is consumed as soon as it entered into the fermenter. Thus, ds by dt equal to 0. So, this is the assumption we can write, that when this equal to less than the mu max value, the limiting substrate I explained that limiting substrate which control the growth of the cell as soon as it entered in the fermenter, and just ds by dt, that will be equal to 0. Now, finally, we have this equation. If you look at previous equation is like this, then this equation we have, then we can write this equation, that dx equal to g into y x by s and dt, and this is integrate from 0 to t. Then in this particular system, so we can have x t equal to the total cell mass concentration is the x0 plus g into y x by s into t. The x t is the total cell mass biomass concentration, x0 is the initial biomass concentration. So, this is how we can analyze this system. Now, that kinetics, that equation, that if you when you take the Monod equation here, mu equal to mu max s, this can be equal to 1 by x g into y x, and we can write again in this form, and from this we can find out the value of this kinetic constant mu max and Ks we can calculate. Now, advantage question comes, what are the advantage and disadvantage of the fed batch process? The higher yield resulting from the well defined cultivation period. So, because I can give the example, the Baker's yeast fermentation process. Baker's yeast fermentation process. Now, in the Baker's yeast fermentation process, what is the stoichiometry we have? We have, suppose we use the sugar as a raw material and sugar converted to cell, am I right? The stoichiometry is that 1 gram of sugar usually converted 0.5 gram of cell. So, if we want to increase the amount of cell production, so what we shall have to do? We shall have to use the amount of sugar input to the system. Now, we have seen before that as your substrate increases in a batch process, but if you increase the substrate, then we find that kind of substrate inhibition. Mu we plot, we have this is no inhibition, and then we have some kind of substrate inhibition that takes place. Now, question comes, that means if you, as soon as you go for the highest substrate utilization, then that the activity of the organism, that will be reduced to a great extent. Now, to avoid this situation, this fed batch process appears to be the better solution. The reason is that since since you are acting in a stepping wise manner, so amount of substrate that is utilized in the system will be more as compared to batch process. Batch process, the same batch process, same volume if you use, and compared with the fed batch process, you can use more amount of substrate. Since you are using more amount of substrate, so you will get more amount of cell mass in the system. So, one particular application we have, that is in case of Baker's yeast. Another example is the penicillin fermentation process. In the penicillin fermentation process, what is happening? That 1 mole of we know that precursor that is required in the penicillin fermentation process is the phenyl acetic acid and phenoxyacetic acid. Am I right? Now, so this is 1 mole of phenyl acetic acid produce 1 mole of that penicillin G, and 1 mole of phenoxyacetic acid produce 1 mole of penicillin B. So, naturally, if you now, since this is acid, if we add all this acid at a time, it will give some kind of inhibition effect on the growth of the cell. That is a major drawback. So, that particular problem, that that if you want to produce more penicillin, so naturally fed batch process might be the one of the major approach. The low level of limiting substrate concentration helps avoiding the substrate inhibition. That is the major facts that we have. What I try to point out, this is substrate concentration and this is time. So, we maintain a particular level of substrate which is below the inhibition level. Then you keep on feeding, and so that your rate of reaction does not hamper. The catabolic repression, when this is an issue in the production process, the catabolic repression, that problem also can be overcome. Avoid the toxic effect of some media components. So, that also can be avoided to some extent, because you are not adding, you are adding only the substrate, that in the stoichiometry, on the basis of stoichiometry you are increasing, you are not adding all the components present in the reaction mixture or in the media. So, naturally the possibility of toxic accumulation, that will be reduced. The disadvantage of this process is a lower productivity level due to high downtime for filling, heating and sterilization, cooling, emptying and cleaning the reactor. So, it will require lot of time for that the downtime will be more, and higher cost in labor and dynamic process control of the process is required. So, this process is not as simple as your batch process. In the batch process, we have seen we take the material at a time, allow it to react. After this reaction is over, you take it out. That this is something in combination of the batch and continuous process. But here we started with the batch mode, then continuously we feed the material in such a way that your substrate concentration always remain below the inhibition level, so that your more product formation take place and you get the products. So in conclusion, what I want to tell you that that as compared to that batch or chemostat or plug flow reactor, the fed batch has some added advantage in the sense that we can use more amount of substrate in this particular fed batch process, and the substrate inhibition problem that can be avoided to some extent. There are two type of strategy that we have: variable volume or fixed volume, through which the fed batch operation can be done. And we showed you how the kinetics of this process can be analyzed. And finally, we discuss what are the merits and demerits of the fed batch process. Thank you.